Question 8. This question about sodium and some of its compounds. Use your knowledge of structure and bonding to explain why sodium bromide has a melting point that's higher than that of sodium and higher than that of sodium iodide. So it's a 6 marker, so it's going to have 3 stages generally. So 3 stages. So why does sodium bromide has a melting point higher than that of sodium? Well, first things first, just talking about sodium. We know sodium has metallic bonding, attraction between positive nucleus and delocalized electrons in sodium. Na, sodium, also has a giant lattice structure. So now NaBr, Nai, well, we know there's stage 2, NaBr or Nai. We know ionic bonding in NaBr and Nai. Attraction between positive and negative ions in NaBr and Nai. NaBr and Nai have a giant lattice structure. So we talked about structure now. Now comparison of bonding, because that's really, we missed this step, we're not going to get more than 4 marks, I don't think. Comparison of bonding. But that's same with any step as well, really. But this step is really key. So we're going to compare the bonding now. And this part is probably the hardest part. Well, we know that ionic bonds are stronger than the metallic bonds. Stronger attraction between positive and negative ions in NaBr than Nai. And finally, why is a stronger attraction between positive and negative ions in NaBr than Nai? Well, since Br minus ion is smaller than the I minus ion. So 3 stages. Stage 1, sodium. Sodium has metallic bonding. Okay. What is metallic bonding? Attraction between positive nucleus and delocalized electrons in sodium. Obviously, basically define metallic bonding and apply it to the question, in this case sodium. And sodium also has a giant lattice structure. Stage 2, NaBr or Nai. Well, there's ionic bonding in NaBr and Nai. Perfect. Attraction between positive and negative ions in NaBr and Nai. NaBr and Nai have a giant lattice structure. Comparison of bonding. Ionic bonds are stronger than metallic bonds. Stronger attraction between positive and negative ions in NaBr than Nai, since the Br minus ion is smaller than the I minus ion. And that is for 6 marks with the 3 stages. Stage 1, Na, Stage 2, NaBr, Nai, and Stage 3, comparison of bonding. And question 8.2, 8.3, and 8.4. So when 250 milligrams of sodium were added to that much of water at 25 degrees Celsius, a gas was produced. Given the equation for the reaction that occurs. Sodium added to water. So sodium Na plus H2O NaOH plus H2 plus hydrogen, but obviously the hydrogen in this case is going to be a half to get 2, because if it was not a half then it would be 3 hydrogens on the right hand side and 2 hydrogens left hand side, which is not correct. It needs to be balanced, so we put a half there. So Na plus H2O arrow NaOH plus a half H2. Na plus H2O arrow NaOH plus a half H2. Now we need to calculate the volume of the gas formed 101 kilopascals. Well, if we think about the ideal gas equation, because that's ultimately what we're going to be using for this question. PV equals nRT. And what we're trying to find is the volume. So we're trying to find V. So V is equal to nRT over P. So now let's tick them off basically. Do we have the pressure? Yeah, we have in kilopascals, so that's 101,000 pascals that we're going to be using. Do we have the temperature? Yep, at 25 degrees Celsius, but obviously we're not going to use that. What we're going to do is add 273. So add 273, and we're going to get 298 Kelvin. Do we have R? Yeah, R is a gas constant. R gives us the question 8.31. It's always 8.31, but it's given us in the question as well. And now the moles. So we need to work out the moles. That's all we need. And this simplifies it. So now I know that all I have to do is work out the moles. How do we work out the moles? We know the mass of sodium is 250 milligrams, which is 0.250 grams. So let's convert this 0.250 grams. Remember, milligrams to grams, you want to divide what's going on, but we divide by 1,000. There we go. And then from grams to milligrams, we times by 1,000. So we've got the mass of sodium. We need to find out the moles of sodium. Well, what is the MR of sodium? It's 23. So moles of sodium is going to be 0.250 over the MR, 23. Remember, it's just sodium by itself. That will give us 0.0109 moles. And now you guys are like, now we just substitute it into the equation, get the value, life simple. No, because now we want to find out the moles of hydrogen. Because it says in the question, calculate the volume of the gas formed. which gas is formed? Hydrogen. This is sodium hydroxide. We don't want the moles of NaOH. We want the moles of H2. That's exactly what we want. So we're going to times it by a half because it's a 1 to a half ratio, molar ratio. So we can times it by a half, and now we get 5.45 times by 10 to the power minus 3, and that's the moles of H2. And now we can substitute an equation, so we get V is equal to 5.45 times by 10 to the power minus 3 times by R 8.31 times by T, temperature in Kelvin, 298, over pressure in pascals, 101,000. Put it on a calculator. And we get 1.33 times by 10 to the power minus 4, but that's obviously meters cubed. In ideal gas equation, volume is going to be meters cubed, and we're trying to find it in centimeters cubed. So what we're going to do is we're going to times what we're going to times by. Well, we got it in meters cubed, so we're going to times by 1.32 times by 10 to the power minus 4 times by 10 to the power of 6. So we're timesing by a million, and now we'll get 133 as a volume. So really important, like your units are half the marks of this question, basically 2 marks already, I'd say. And if you don't get it right, you're not going to get a correct answer, you're going to lose marks. However, it says in the question, calculate the volume in centimeters cubed of gas formed at 101 kilopascals in centimeters cubed, which we just worked out, so it's going to be 133. So that final trick really catch people out, including myself. You know, volume measured meters cubed for PV is equal to NRT, so you need to times by a million to get into centimeters cubed. And now 8.3, calculate the concentration of sodium ions. Well, we know moles is equal to concentration times volume. Concentration is equal to moles divided by volume. And there's a lot of stuff going on in this here, so yeah, so let's write that down. Moles is equal to concentration times by volume. Therefore, we're trying to find concentration. Instead of writing it down, the equation, it's a 1 marker, so I'm just going to substitute values in. It's going to be moles of Na, which is 0.0109 over volume. Now it's not volume of this, it's total volume, which is 500 centimeters cubed of water, but it's also in mole per dm minus cube, so it's going to be 500. To get from centimeters cubed to mole per dm minus cube, we can divide by 1000, so 10 by 10 to the power minus 3, and that will give us 0.0109 all over 500 10 by 10 to the power minus 3, 0.0218. And you can already see now questions are getting extremely hard. Enter the units, convert between units, that much for one marker. Not too difficult, but still tries to trick you out. So please, if anything you can take away from this video, just a separate video, is learn your units like very confidently, and also what volume is it for ideal Gauss equation, what's meters cube, etc, etc. And now final part 8.4. Sodium reacts with ammonia to form a compound NH2 that contains this ion. Draw the shape of this ion, include any lone pairs of electrons that influence the shape with 4 marks, and then predict the bond angle, justify a prediction. So NH2 minus ion, so it's going to be NH, and because it's a negative charge, I have square brackets around it, and a negative charge here because the negative charge, NH2 minus ion. Now, is it going to have lone pairs of electrons? That's the question. Yes, it will. It will have 2 lone pairs of electrons. Nitrogen is in group 6, pretty sure. Double check now. What group is nitrogen in? Yeah, it's in group. No, it's in group 5. So it's going to have 2 lone pairs of electrons. Think about it. Bonded to 2 hydrogens. But you're also going to add an electron because there's a negative charge. So yeah, it would have 3 electrons, but now it's going to have 4, so therefore 2 lone pairs of electrons. The bond angle, well, it's got 2 lone pairs of electrons, NH2. It's going to be 104.5 degrees. 104.5 degrees, and the justification, well, because electron pairs repel each other to be as far apart as possible. Electron pairs repel to be as far apart as possible. Or you could say lone pair repulsion is greater than lone pair bonding pair repulsion. But this one is, an answer I always see in a mark scheme. They really like to put this in a mark scheme. Electron pairs repel each other to be as far apart as possible. That is the end of question 8.